This is Facility Science Podcast number 24. I am Jason Doolittle, and today I'm talking about elevators. This is elevators part 2 because I didn't get through all of my elevator notes last time, and this is a continuation of elevators part 1, which is number 23 of this podcast, so you might want to go listen to number 23 before you continue on with this one. And this is going to be about some of the safety mechanisms that are built into our modern elevators. And modern passenger elevators are very safe when properly operated and maintained, so we're going to see why in the next 20 or so minutes. So there are many safety mechanisms associated with modern elevators. Some of the safety mechanisms are electronic or logical, meaning they're a function of the elevator controller or electronics. And other safety mechanisms are mechanical in that they operate independently of the controller based on the motion of the elevator or the disposition of the elevator components, and in some cases even without electric power or due to the loss of electric power. And I also think of elevator safety mechanisms in two other categories, and these are safety mechanisms related to the doors and safety mechanisms related to the car falling. And so safety mechanisms related to the doors prevent opening of the doors while the car is not properly leveled at a landing, or they prevent any movement of the car while the doors are open. And safety mechanisms related to the car falling work to prevent the car from, say, crashing into the pit at a speed high enough to kill the passengers, or potentially crashing into the top of the hoistway if you have a situation where the counterweight is much heavier and the elevator falls upward, which can happen. And I read a good article about this from Otis Elevators, and it looks like it might have been in a magazine at one point, but I read it on their website. And the article is titled Safety Chain, with the subtitle, A Look at Safety Systems in a Modern High-Rise Elevator in Light of the 2018 Chicago Incident. And I'll reference that article a little bit here, and also I'll link to it in my notes at facilityscience.com. This is number 24. And the 2018 Chicago Incident, referred to there in the subtitle, is, and this is reading from the article here, in late 2018, an express elevator in a Chicago skyscraper was traveling down from the 95th floor to the lobby when it came to an unexpected stop away from a landing. Investigators found out that one of the elevator's 7 suspension cables had broken, likely as the elevator was passing the 20th floor. The car slowed to a safe, controlled stop between the 12th and 11th floors. The 6 passengers inside were unhurt. The incident immediately generated sensational media headlines variously claiming that the elevator at 875 North Michigan Avenue, formerly the John Hancock Center, had plummeted, plunged, or fallen 84 floors. It hadn't. And unfortunately, they left out the Oxford comma in that last sentence. So the article then goes on to explain that the elevator didn't actually plummet or plunge or fall 84 floors from the 95th to the 11th, but instead came to a safe, controlled stop in 8.5 floors. That's from the 20th to the 11th, exactly as designed because of the safety features designed into the elevator, which of course is exactly what an article written by an elevator manufacturer would say, but it is a good article and very concisely explains the mechanisms involved. So like I said, link at facilityscience.com in the notes for this, number 24. So the safety chain, which is the title of that article, and you might also hear engineers or elevator mechanics talking about something called the safety chain. And the safety chain is a concept that the elevator system monitors a number of different conditions that indicate the elevator is safe for passengers. And this is the safety chain. If any link in the chain is broken, meaning that some operating parameter is abnormal, the elevator system takes steps to stop the cab in order to keep the passengers safe. And I've seen this safety chain term used in slightly different ways, but the idea is always the same, just sometimes more or less abstract. So now let's talk about the safety mechanisms related to the car falling. And these things are mostly relevant to traction elevators rather than hydraulic elevators. And I'll take them in the order from the Otis article about the elevator in Chicago. There's also a good infographic in that article if you're interested in a visual representation of this. So first we have the controller. And the controller, that's the computer or circuitry that's actually controlling the elevator. The controller can monitor many things potentially, but in the most basic case, it might monitor the speed of the elevator. And it can actuate the speed of the traction machine motor to adjust the speed, in this context, to slow down the speed of the traction machine, the motor, if the car is moving too fast. The controller could also activate some of the other safety mechanisms if it can't get control of the car's speed just by adjusting the speed of the motor. Okay, so we also have the traction machine itself. The traction machine can act as a safety mechanism in that it can be slowed down in order to slow the car down. So you have that friction of the ropes, the cables over the traction sheave. And so if you can manage to use the motor in the traction machine to restrict the motion or the spinning of that sheave, you can potentially slow the car down. There's also the brakes, machine brakes, and this is a brake that's built into the traction machine that can stop the sheave from turning. And this is similar to the disc or drum brakes in a car. The brakes can be applied by the controller if necessary. So there's an output from the controller that says, hey, put the brakes on. Also, the brakes are held open electrically. So if power to the elevator fails, the brakes will be applied automatically because there's no longer being held away from the sheave or from the whatever the contact surface is by the electrical mechanism that actually keeps the brakes from activating. All right, next we have a device called a governor, and the governor is a device consisting of a sheave and a cable, and the cable is called the governor rope. And it's actually two sheaves, one at the bottom of the hoistway and one at the top, but the actual governor device itself is usually at the top. And these sheaves and the governor rope are completely separate from the traction machine and the hoisting cables, and the governor rope is also attached to the car. So the governor rope just goes around and around the two sheaves as the car goes up and down. And the governor's job is to detect when the car is moving too fast. And it does so by spinning as the car is moving, because as the car moves, it pulls that governor rope around and spins the governor sheave. And the faster the car is moving, the faster the governor rope will move over the governor sheave. And when the governor gets to a certain speed, centrifugal force will cause some type of a weighted or spring-loaded mechanism to spring outward, activating the governor mechanism. And the governor will engage the machine brakes. So now we have three different ways the brake can be activated. And also the governor will engage the car safeties, which I'll talk about in a minute. And the safeties are engaged mechanically, so no electric power is needed for this. When the governor overspeed mechanism trips, the governor rope is stopped because the centrifugal force made the weighted or spring-loaded mechanism fly out and stop the governor sheave, which stopped the governor rope. And since the car is presumably still moving at this point, or the governor wouldn't have tripped to stop the rope, the governor rope will pull on the safety lever on the car, causing the safeties to deploy, right? The car's still moving, the governor rope is stopped, so that stopped rope, when the car continues to move, will pull a lever, deploy the safeties. The safeties are a device mounted on the car and riding on the guide rail, so it's part of the car assembly. When the safeties are engaged, they grip onto the rails and bring the car to a stop relatively quickly. And in case I didn't make it clear enough, the operation of the governor and the deployment of the safeties is an entirely mechanical process. This doesn't involve the elevator controller in any way or even require any power. It's all completely mechanical. And then finally, at the very bottom of the hoistway in the pit, we have the buffer. And I talked about the buffer a little bit in part 1. And the buffer is there as sort of a last resort if all the other safety mechanisms fail to stop the car before it reaches the bottom. So the buffer is some type of a hydraulic spring designed to absorb or otherwise dissipate some of the energy of the falling elevator car. In case it has some energy left, hasn't quite been able to stop yet, it'll hit that spring at the bottom and compress it, which will hopefully be able to take enough energy out of the falling car in order to not cause death or serious injury to the people that are inside of it. And in addition to these explicit sort of safety mechanisms, we can also count the hoisting ropes and maybe even the counterweight as a safety mechanism. So elevator ropes are highly redundant, so the car won't fall even if most of the ropes break. And in many scenarios, the balance between the car and the counterweight, this is again in a traction elevator, will slow any possible acceleration, which means that the car will take longer to reach dangerous speeds, longer than it would if there was no counterweight. Now, other than the buffer, that's that spring at the bottom that'll try to catch the car if it falls all the way to the pit, The safety mechanisms I described here don't apply to hydraulic elevators, which is most elevators. I read somewhere that something like 75% of all elevators in the US are hydraulic elevators, which makes sense since most buildings with elevators are less than 8 floors, which is sort of the upper limit for a hydraulic elevator. And the reason why hydraulic elevators don't have and generally aren't required to have these fall protecting safety devices is partially because they don't go as high or as fast as traction elevators. So there's less distance to fall, and less speed means less energy in any collision. Another big reason is that a hydraulic elevator doesn't hang from cables. Instead, it's supported from underneath by a hydraulic piston, making actual free fall nearly impossible. Also, a hydraulic elevator can't fall upward, unlike a traction elevator where the car can fall upward if it's lighter than the counterweight. Most of the time, a failure in a hydraulic system will be caused by a leak of hydraulic fluid, with the result being that the elevator car sinks slowly. This can be a safety issue because it can cause misleveling of the car, meaning that after the car stops at a landing and opens the doors, the car will continue to sink a little bit because there's a slight leak of hydraulic fluid, creating a trip hazard and much more rarely a crushing hazard. But it would take a catastrophic failure of the hydraulic piston to cause a hydraulic elevator to fall into the pit with enough speed to actually injure people. And most commonly, this happens when the bottom cap of the cylinder, the hydraulic cylinder, breaks out, causing the hydraulic fluid to leave the cylinder fast enough for the car to gain some speed. And this is rare, but it can happen and might actually be inevitable if an elevator is operated for long enough. The failure is caused by a combination of corrosion and repeated stress on the steel. So the longer a piston is operated, the more likely this type of failure is to happen. Now, newer cylinders, these are ones that were made after 1971 or 1972, have a safety feature intended to prevent this type of catastrophic failure. So they add another bottom plate inside the bottom of the cylinder. This one has a small hole in it so that if the actual bottom of that cylinder were to break out, the oil couldn't just all spill out the bottom of the cylinder. It would have to get through the small relief hole before leaking out the bottom of the cylinder. And these are called double bottom cylinders. And the relief hole is sized to limit the falling speed of the car to something like a safe level. And if you want a visual representation of this, it's kind of maybe hard to picture just by my words here. There's an article from Kone Elevators, Kone, that has a good diagram. And Kone is an elevator manufacturer, so the article is also partially a buy our product to solve this problem kind of thing. And you can find a link to that article in my notes at facilityscience.com. And this is number 24 about elevators part 2. So if you have a hydraulic elevator that was installed prior to 1972, you might want to make sure that it has been updated with a double bottom cylinder. Okay, now I'll talk about some safety mechanisms related to the doors. Maybe the most conspicuous door safety device is the sensor on the edge of the door that keeps the doors from closing when something is in the doorway. And this is both for accessibility purposes and also for safety purposes. From the accessibility angle, if someone is still in the doorway when the door is closing, that might mean they need more time to get in or out and the door should stay open. From the safety angle, if there's someone in the doorway, that means that the person is in between the car and the landing, the hallway, which is an extremely dangerous place to be if the car were to move. And having the door remain open should prevent the car from moving. And if the car moves away, the person at least won't be trapped in between the doors and might have a chance to get out of the way. This type of device is called a safety edge or door edge detector or something like that. And there are a few different types of this mechanism. The older type is a mechanical bumper. So when the door hits something, the bumper actuates a switch that causes the door to reopen. And these used to be very common, but are largely being replaced by newer and supposedly more reliable technologies, and also that don't require physical contact with the door to trigger them. These newer safety edges use infrared beams across the door opening. So there is an emitter, an infrared emitter on one side, and then a receiver on the other. And so if the infrared beam across the doorway is broken, the door won't close. And these sort of started out with 1 or 2 IR beams across the opening and have evolved to effectively cover the entire door opening with what they call an infrared light curtain, term you'll see in the marketing and terminology. And they're even what they call 3D light curtains, which detect movement or objects immediately outside the doorway. And so these things basically keep the door from closing when they shouldn't. And we're also very concerned about keeping the doors closed when they shouldn't be open. So there are safety mechanisms that only allow the doors to open when they should open, which is when the car is properly lined up at a floor. So there's a lock on the car door that can only be opened from outside the car. And there's a lock on the hoistway doors that can only be opened from inside the hoistway. And basically this means that the doors can't be opened from the places where the people are. And maybe we should say can't be opened without special tools and knowledge, because there are ways to get the doors open if necessary. So these door locking mechanisms are disengaged when the car lines up with the hoistway doors. So on the hoistway side of the hoistway door, there's some rollers called pickup rollers. And these pickup rollers are attached to a lever mechanism that actuates the hoistway door latch. So basically, if you pull on the lever, the hoistway door latch lifts up, which can only be done from inside the hoistway. And there's a device called a clutch on the outside of the car doors that lines up exactly with the pickup rollers on the hoistway doors when the car is aligned at the floor. So when the car door clutch engages with the pickup rollers, the lever mechanism attached to the pickup rollers lifts the hoistway door latch, unlocking the hoistway doors. And this alignment also disengages the lock on the car door, allowing the doors to open. And the details of exactly how the car door unlocks and under what circumstances the elevator controller will actually initiate door opening varies by elevator, but the concept is generally the same. The device that keeps the car door closed is called a restrictor. And in some cases, there'll be the main lock on the car door that's disengaged by the mechanical action of the car door clutch lining up with the hoistway pickup rollers. And there might be an additional restrictor added to the car door that will have some sort of electromechanical operation to it. And I should also mention, because I don't think I did before, that the actual door opening mechanism is an electromechanical device on the car called the door operator. And the hoistway doors generally don't have their own opening mechanism, but instead are just pulled along by the car door due to the engagement of the car door clutch with the pickup rollers on the hoistway doors. So the opening of the doors is all done by that door operator on the car. And there are also devices that attempt to prevent the car from moving when the doors are open. And the governor that I talked about before sometimes can perform this function. The governor can be engaged while the doors are open. So if the car moves, the governor rope, being held stationary by the governor, will deploy the safeties to stop the car movement. Another device that's used to prevent the car from moving while the doors are open is called a rope gripper. And the rope gripper acts as another type of brake. And what the rope gripper does is it will grab the hoisting ropes to prevent the car from moving. And these devices don't generally, again, apply to hydraulic elevators. I had trouble finding the details of mechanisms that prevent a hydraulic elevator from moving. I mentioned earlier that, say, a slow leak in the hydraulic system of a hydraulic elevator can cause the car to sink after the doors open. And so we want something to prevent this. And like I said, I wasn't really able to find the details of any of these mechanisms about how they work. You know, there's some valving mechanisms that could do this, some rail gripping mechanisms. But again, unfortunately, I wasn't able to find some hard details. If I do, maybe I'll add them in a sort of a later episode here. And I still have a little bit more about elevators in my notes. So it looks like there'll be an elevators part 3. I'm not really quite sure how this happened. I didn't intend to spend this much time on elevators. One last thing I want to say about this. And I said before that modern elevators are very safe when operated and maintained properly. And it's our responsibility as the facility management professionals to make sure that happens. We have regulations and we have inspections by our local government building departments, but those inspections and regulations are not meant to protect the building occupants from faulty elevators. That's our job. The inspections are meant to protect the building occupants from negligent building owners and facility managers. We know what it takes to keep the elevators safe, whether we get inspected by the government or not. So even if we have maybe, say, an understaffed building department that can't get around to do all the inspections, which is the case in quite a few places around the world, or we have lazy inspector that phones the inspection in from the truck, we still owe it to the people that live and work in our buildings to make sure that the elevators are safe, regardless of whatever sort of oversight body happens to do with respect to our building. It's our job. So I think that's all I have to say about elevators for right now. Like I said, there's going to be a part 3, I guess. Not sure how that happened. You can find my notes for this, which will have links to those two articles I mentioned at facilityscience.com. This is number 24. If you have any questions or comments about this topic or suggestions for other topics you'd like to hear about, you can contact me by email at podcast@facilityscience.com or at facilityscience on Twitter. If you like this podcast and you want to help me keep making it, you can head over to facilityscience.com/support and see if any of the support options there appeal to you. Right now, there's a link to Amazon.com there. So if you click through that link and buy something from Amazon.com, they'll give me a small percentage as a referral fee at no additional cost to you. There's also a PayPal donation option there. And so I hope you find this useful, and thanks for listening.